All right, good day and welcome back to the Statistics and Mathematics Teachers course on stochastic processes. So, in today's video, we're going to look at a continuation of our queuing system course. Okay, so today we'll be focusing on transient and steady state. So, a system is said to be in transient state when its operating characteristics or behavior are dependent on time. So, here we are trying to say that the average waiting time, the number of customers in the queue, and then like in the system, and all these operating characteristics plus the probability distribution of the arrivals and the waiting time are all time dependent. Usually, if these are time dependent, as in is in transient state, it becomes very difficult for us to know the long run behavior of the queuing model. Okay, and as such, we want to stabilize this queuing model by making it a steady state. So when the system settles down as a steady state, the arrival of a customer is less than the service rate and are both constant. So what we are trying to say here is that for a queuing model to be in steady state, it means that its operating characteristics are not time dependent. They do not depend on time. Okay. So meaning the probability distribution of these arrival and the service rate are not time dependent. So as such, we can determine or we can calculate the long run behavior of the queuing model that we are using. Okay. Yes. So let's try to move on and you understand this better in the subsequent slide. So we know that if we let x denote the number of customers in the system at a time t, and Pn should be the probability that we have n customers in the system. So we know that in a Poisson process, that is the arrival. This looks like a Poisson process. Once we are talking about the number of customers in the system at a fixed interval, then it is as a Poisson process. That is probability that x of t is equal to what n arrival. So, but this is time dependent because the time at which this is happening, because this is a process, so a process should be time dependent. We don't want this to happen because if it is, then it means that it will be a challenge to study the long run behavior of the queuing model. So we take the limit as the time approaches infinity. If this preceding limit exists, then it means that we are in steady state. So in other words, Pn, you see that after we take the limit, the t has vanished, leaving us with Pn, meaning the number of customers in the system is not time dependent. So Pn is the limiting or long run probability that there will be exactly n customers in the system. Okay, it is sometimes referred to as the steady state probability of exactly n customers in the system. So take note of this. Okay, yeah. So that is what we can do to a queuing model to make sure that we do accurate predictions and calculations about our average customer queue length, average system length, average service time, and those stuff, right? Yeah. So let's look at a general way that globally, mathematically, we can put queuing models some notations to denote all the characteristics of a particular queuing model. We have a lot of queuing models. So no matter the queuing model, what are the notations that we can use to look at the characteristics that every queuing model should have, or the focus that we need to put on in studying queuing models? So we normally put it in Kendall and Lee notations. These notations are symbolic forms, okay, in the following pattern. So it helps us to know the arrival pattern. So the first symbol A is the arrival pattern. That means we have gone through this in the previous video. Okay, so the arrival pattern is A. The service time. So how do like the customers get served? How's the service pattern like? Is it first come first serve, first in, and so forth? That's the service pattern. So the number of channels, as in C is the number of channels. How many channels are available, or how many like queues? Okay, and we have D as the capacity of the system. Is it going to be finite or infinite? Okay, and the order of servicing is E. Okay, the order of servicing. So I've explained all this into detail. So now when you see M, we normally use the M to denote the first A. When you see M in place of the first A, it means that the arrival time follows Poisson distribution. Okay, and if M is used in place of the D, that's the service pattern, that means that it follows an exponential distribution. Let me move on to the next one you see. So whenever you see M in the Q model, I've explained these things already. The M and the first M and the second M, right? Yeah. So that's why I kept emphasis on this slide so that we know what the first M and the second M is when we replace it with A and B respectively. All right. Yeah. So let's look at an example of a QU model. So I'm going to look at the MM1 exponential QU model. As we all know, the first one indicates that arrival pattern follows Poisson, and the second M shows that the service pattern follows what the exponential distribution. Of course, we have a single channel because this is one single service model. It means that like this can be seen in the ATM machine case. When we have ATM machine, it's only one ATM, so one person can use it at a time. So the servers are one. Okay, so infinite means this is the capacity of the system. So it means that the system can contain as much as any number of elements or customers that we can have. So this cannot be applied to human beings because in the human beings case, we know that even the world's population is known, right? The world's population is known. So there's no way where like we have infinite human beings. So this can be seen in elements, even as of elements. Yeah, sometimes it can be, yeah, in rare cases. Yeah. So and it's first come first serve. This is the service pattern. Okay. Yeah. So first come first serve. All right. That's the exponential QE model. So we're going to use this QE model as our reference model to study all the operating characteristics of a queuing system, right? So stay tuned and let's continue. So now, a generalization, sometimes we generalize these like Kendall and Lee notation. Okay, so when we see the first M, we know that this is Markovian or exponential, indicating the interarrival times and also the arrival, the service time as well. So the D, if you see D in a QE model, it means that the D is a constant or deterministic interarrival time or service time. Okay, yeah, so G is the service time, that's departures. Okay, when we serve you, we expect that you should depart from the system, or in other words, you exit. Okay, yeah, so GI is the interarrival times having a general probability distribution such as normal, uniform, or any empirical distribution. Okay, yeah, so the Erlang distribution, remember I mentioned this in the Poisson distribution case. When the k takes integer values, then the gamma distribution becomes the Erlang distribution. So when you see E as with k, it means this is the Erlang. It means that the interarrival or service time follows the Erlang distribution, with the k being the k is the Erlang is the what as k approaches infinity, the Erlang approaches deterministic. Yeah, so yeah, the Erlang constant, that is the k. If k is equal to 1, the Erlang is equivalent to the exponential. Remember I've mentioned this. So if you have k to be 1, that means that the gamma or the Erlang distribution becomes the exponential distribution. Don't be confused. Alright, so remember I told you this is a complete course. So we are taking the concept and adding them up. So don't get confused as some of the things we use, because I've already mentioned this Erlang, and then when k is equal to 1 is exponential. Thank you. So let's look at the single server exponential queuing model. So this one we've already looked at it, right? That's the model we've introduced before. So here we say that there's a single server at the station according to, and then the number of customers arrive according to a Poisson process. That's the arrival rate follows a Poisson process with rate lambda. So the Poisson, remember the rate of the Poisson distribution is lambda. Okay, so that is the time between successive arrivals are independent exponential random variable having mean 1 over lambda. Remember the mean of the exponential is also 1 over lambda. So this is a service rate or service time distribution. So it follows exponential, and the arrival follows what Poisson process or distribution. Okay, yeah. So we've looked at most of these things. Let's move into this. So let's look at some of the assumptions of this QE model. Even when you look at this model, you can tell most of the assumptions from here. You realize that the arrival follows Poisson distribution. That's an assumption. The service time follows exponential, there's only one server. There's infinite capacity of the system. Okay, infinite. So these are all assumptions you can mention. So don't be confused. And you can also see that it's served. Arrivals are served on uh, first in first out basis or first come first served basis, right? So every customer awaits to be served regardless of the length of the queue. So here we assume that there's no banking, there's no reneging and those kind of like customer behaviors, right? And arrival of customers are independent of one another. So if Kwaku goes to the bank today or arrive at the bank today, doesn't mean that Kwaju is also going to arrive or Amina will also arrive. So they are actually independent. Arrival of customers are assumed to be independent. And also, yeah, so I've mentioned that arrivals are described by a Poisson distribution and come from an infinite or very large population. Yeah. So the assumptions continue. So service time vary from one customer to the other. Yeah. So service time are not the same. So service time occur according to a negative exponential probability distribution, which we've already seen. I've mentioned that one. So the average service rate is greater than the average arrival rate. So let's understand this. So if you have a system or maybe an organization where you have maybe in the bank, when there are three tellers, then you have three servers. Okay. So if the rate at which the servers are serving the tellers are serving the customers, it's actually less than the arrival rate to the service center. It means that there's going to be pressure on the service, right? So that is not good at all. So in your business, it's very good for you to have the service rate to be greater than that of the arrival rate, such that there will not be pressure on the service, right? So the service rate should be greater than the arrival rate, such that like the service should not be prone to making mistakes. Imagine in a financial system where you are dealing with money and there's pressure on the service. You're going to lose money because they'll make mistakes and then your money may be given to somebody by accident. Okay, yeah. So let's try to now look at the operating characteristics of a QE model. So now some preliminaries and terminologies. Let's look at the notation. So when you see S in a QE model, so we're trying to say that this is the number of parallel service channels in the system. So S is mostly referring to a system. And when you see Q is referring to a queue. Remember I told you that system length should be equal to the queue length plus the what? The service length, right? So a system is mostly denoted by S and then the queue is Q, right? So LS means the average number of customers in the system and LQ is the average number of customers in the queue. So average waiting time in the queue is WQ, right? And average waiting time in the system is WS. That's the notation. So N is the number of customers or units in the system. Note that. And this steady state probability, we've already looked at it, of having N customers in the system. So lambda is the average number of customers arriving per unit of time when they are already N units in the system. So it means that if you have N customers arriving, that means that each rate, the arrival rate for each of them is what? Is lambda. But when you sum them up, like that's going to give you lambda N. So lambda N, they're having N customers in the system. So their average service arrival rate is what? Lambda N. So, but when you take it to be a constant, as in if lambda is constant, as in first customer coming, the first one means that for the arrival rate of the customers, they are actually different. Okay, yeah, the average arrival rate, or yeah, the average arrival rate is different for all the customers, the end customers. But with this one, we're trying to say that it's constant, as in the first customer arrives with a rate lambda, the second customer arrives with the same lambda, so constant. So the same thing will apply to the service rate as well. So mu n means that when we have different service time for all the customers, right? And mu actually means that it's a constant rate for all of them, service rate. So 1 over lambda is actually the inter-arrival time. So we know that follows exponential. And inter-service rate, or the time between the service of customers, is also 1 over mu, right? So rho is the traffic intensity or utilization factor for the service. So we're trying to say that rho is how it determines how busy the system is going to be. How busy are the servers? That is rho. Alright, that is rho. How busy are the servers? So rho will be equal to the service rate divided by the arrival rate. That is lambda over mu. That is that, right? So n is the maximum number of customers allowed in the system. So don't be confused. So let's look at the rate balance principle. So I'm trying to say that the rate at which It says that the rate at which the process enters state n, it should be equal to the rate at which it leaves state n, right? So now let's make our equation. So this rate balance principle help us to know the probability that we have some number of customers in the system. So it is to help us generate or have a general formula for that of the steady state probabilities. Okay, so let's say that this we have state 0 and state 1 considering these two states only, right? So state 0 and state 1. So state 0 means that there's no customer in the system, and state 1 means that there's only one customer in the system, right? So under what condition can we have no customer in the system, right? We can have no customer. We can have no customer if and only if there's only one person in the system. Okay, there's only one person in the system, and this person gets served, and we have nobody. You get it? So the process can leave state 0 only by an arrival. You can leave state 0 only by an arrival which occurs at a rate lambda when the system is in state 0 with probability p naught. You see that? So resulting in departure rate of what? Lambda p naught. You understand? So it means that how do we be in the state of having no customer in the system? It means that if somebody arrives to the state of we having no customer, that's by a departure. This around whenever you see lambda, it means that somebody is arriving into the system. So you arrive into the state of nobody being in the system. You understand? That is one condition. You arrive and then there's nobody. You are the first person coming. So when you arrive, the state you met is that nobody was there. So you are the first person coming. So you are incoming. You are yet to come and arrive in the state of we having nobody. You get it? So the other way to look at it is that there can be one customer, as I mentioned, one customer in the system, and the person, for us to have no customer in the system, there's supposed to be a departure, meaning that person should have been served. The ATM, if you're using the ATM machine, for us to have nobody, meaning that person should be done with service. And how will that happen? That means the service rate you apply. You were having one person and the person just received service at a rate mu and the person has exited. Okay? Yeah, so that's what I've explained here. So rate out of state 0 is going to be what? Lambda p naught and this. So when you add the two of them, those are the two possibilities we can actually have no um, customer in the system, right? So the two must be equal. So using the rate balance principle. So remember we said that the rate balance principle says that the rate at which you go out and enter the same state is what equal. So that means that lambda p naught should be equal to a mu p1. And when we, this is our first steady state rate balance equation or probability. Okay, let's look at state 1 analysis. So under what condition can we have one person in the system, right? So we know that this can happen if there's an arrival and or a departure, right? Good. So it can be that maybe I've arrived into the system, like I'm the first person to come into the system. Nobody was there, so I'm coming. So I'm arriving from I'm the first customer, so I'm arriving into the system. So yeah, so once I arrive, I come with an arrival with lambda, or there can be two people in the system and one person has been served. So once the person leaves, the service rate is going to be mu, and that will be mu p1, right? Or the other way to look at it is that state 0, we may be at state 0, okay? So with this one, it's like this. It's like a continuous movement. The first one, the continuous movement. Maybe there's one person in the system, all right? There's one person, or two. So there's one person. So the person receives service, and about to once the person receives service from this side, that's the first condition. You receive service, you are supposed to like exit, and there will be no person in the system, right? But the moment you leave, you are about to leave, another person replaces with an arrival. This mostly does not happen in situations where we have human beings. For instance, a machine works, maybe a pure water production machine. You see, when you look at the way they do it, it's like a continuous process, like prrr, pa, prrr, pa. The moment one leaves, the other one enters. So you don't even realize that small time between the departure and the arrival of the new one. So there will still be the state of just one person or one element in the system. So that's what happens. So arrival is like it's like a continuous process. Arrival and departure happens within the same time space, and that is why we are having this one, right? All with p1, all right. Yeah, so the second one is to look at it this way. Maybe there's nobody at all in the system and one person has just arrived. Once the person arrived from state zero, like into state one, maybe state one means one person. So arrival. So once this person has arrived from the state of nobody in the system to now one person, that means we are in state one. Or there can be two people in the system. So two people are there and one person gets served. And then once the person served via a departure. So it means via a departure, once the first person, the second person gets served, there will only be one person, and that person will go with an arrival rate of about mu, right? So that will give us this as well. And using our rate balance principle, when you this one should equate to this, right? Yeah, it should equate to that. So when you equate the two, you realize that generally when we move on, see this, when I equate this, you realize that mu lambda plus mu p1 should be equal to lambda p naught plus mu p2. Okay, so we can look at that to generalize. So look at this, that's the same kind of thing. So we can use n minus 1 and n plus 1 to represent p naught, p1 and p2. Okay, that is just that. Okay, so equation 1 actually is a set of equations, right? Remember over here, n can never be equal to I'm coming. Yeah, so n should be greater than or equal to 1, right? Yeah, n can not be 0 over here. So for n being 0, we have our first rate balance equation, which we had before, the first one. Okay, yeah. So this equation 1 is actually a set of equations depending on the n value that you take. Okay, it's a set of equations, right? Good. So now, P1, making the subject from the first rate balance equation, P1 should be equal to a lambda over mu P naught. Remember, so lambda over mu is the traffic intensity, that's rho. So rho is actually lambda over mu. So we can say that P1 is equal to what? Lambda over mu, that or rho P naught, right? Yeah, good. So with this, we can make Pn plus 1 the subject, and by doing that, you can nicely do this. So we're also going to set P naught equal to P naught. So we don't know what P naught is yet, right? So P1, as we know from here, P1 is equal to this. So let's look at P2. It's just like making to get P2, we have to make n equal to 1, right? So that will be P2. Okay, then we make a subject. Once you make the subject, you realize that we're going to have yeah, so this is P1, we know P naught, and P1 can be seen in terms of P naught, right? So we know P1. So let me go back here. So P1 is what? Lambda over mu P naught. So just substitute that one inside and simplify. You get what? Lambda over mu P1, right? So we can put that in terms of P naught. We want to put everything in terms of P naught, and that will be what? Rho squared, which is lambda over mu squared P naught, right? So we do the same thing for P3. We realize that it's also rho to the power 3 P naught, right? P4 also be rho to the power 4 P naught, right? So meaning Pn should be equal to rho to the power n P naught, and Pn plus 1 should be what? Rho to the power n P naught, right? You can see that everything is in terms of P naught. What is P naught? We need to find P naught, right? Good. So to find P naught, remember P naught is actually a probability mass function for all the customers we have in the system. So we say that when we sum P naught to P infinity, no matter the number of people we have, this is sum to infinity. We sum it to infinity and equate it to 1. We know that when you sum a PMF over its possible domain, you're supposed to get 1. So we use that condition to find P naught. So once we sum with this, you realize that P naught is a constant. We can pull it out. This is like a geometric series. Alright? A geometric series. So the first one is going to be rho to the power 0. That will be 1 plus mu lambda over mu plus lambda over mu all squared plus lambda over mu all cube. So this is like with a common difference of what? Lambda over mu. So we can simply look at that. You see, this is sum to infinity. So we apply the formula nicely here. We obtain equation 2. Now let's make P naught the subject. P naught should be equal to 1 minus lambda over mu, which is lambda over mu is rho. So 1 minus rho. Okay. So our Pn now will be equal to this because we now know P naught. This was rho to the power n P naught. Now P naught is known, so we can substitute it in terms of rho, and we get rho to the power n times 1 minus rho as our Pn. Okay. Now the next to look at is our performance characteristics. Okay. Yeah, but I'll pause here, and then in our next video we look at the performance characteristics. Thank you so much for watching.